I lost my video there. I'm going to have to split it up into a couple of videos. I was going to say, why don't we look at wood on dry snow, just as an example. So it's kind of like as if you maybe had a toboggan and it was a nice cold day and the snow was not melting at all. So you can see if you look over here at the side that there are two coefficients of friction, and they're both for wood on dry snow. But the condition here that's different is at the top of this column it's coefficient with an S, and at the top of this column it's coefficient with a K. And you can see how the number drops just slightly. The static coefficient is 0.22, and then the kinetic coefficient is almost the same. It would still round to 0.2, but it's slightly less, 0.18. And that's just a visual representation there of how if you were trying to push a toboggan across snow and it was stationary, it would be slightly more of a sticky connection between the wood and the snow than if it was already in motion and it was going down a toboggan hill. Okay, I think that's it for the preliminary notes. So what we're going to do is we're going to go on and we're going to do two examples together. Well, let me get my focus going here. We're going to do two examples together, and what I want you to remember doing these examples is you're past that point in your education where you're going to read a question and you're going to know how to answer it right away. This is not that kind of subject, so we're going to put some things together here. We're going to put a whole bunch of ideas together, and when you first read this question, you're not going to know how to answer it right away. So let's see what it says. And I know you can read this. I'm not going to zoom in because I can't fit this whole sentence on the screen, but a 50 kilogram piece of steel is being pushed across a dry steel surface. And those two words are going to be important later. A dry steel surface. And there's an applied force of 520 newtons. And the question's asking, what will be the actual forward acceleration of the steel? Alright, so if I go to the diagram, here's what I'm going to label right away. There's a force forward of 520, but I don't want to leave that as just a number on the page. We want to identify that because that's not the overall net force. That's just the applied force. So that's the forward push due to muscle power or engine power. See, it's really important to make that understanding because where we're going at the end of this question is we're only going to do one calculation at the end. We're going to do acceleration equals what it always equals. Net force divided by mass when you rearrange Newton's second law. So we're going to take whatever the net force is and we are going to divide by 50 kilograms, and that's it. We're going to have the answer in the end. So it's going to be a really fast calculation at the very end of this page. But we have to determine the net force, and 520 is not the net force because there's a connection here between the steel and the steel, and on the opposite side opposing the motion there's a force of friction. So we need to determine the value of the force of friction so we know how much to take off of the 520. Force of friction has a formula: coefficient multiplied by normal force. Now remember, normal force is not net force. Normal force is the ground pushing up on the object.